the fascinating field of photovoltaics, generating power with sand and the sun. Capturing solar energy is the end result of complex chemical and physical processes. As a first step, raw silicon is extracted from quartz sand. For use in the photovoltaics industry, the semi-metal must be 99.99% pure. To generate solar power, the photovoltaics industry utilizes the semiconducting properties of silicon. In special ovens, raw silicon is melted at temperatures of over 1,400 degrees centigrade. A thin rod, known as the seed crystal, is then submerged into the liquid raw silicon and pulled back up very slowly. At this step in the process, the liquid silicon accumulates on the seed crystal and solidifies. Over 4 days, a silicon rod of up to 2.8 meters length takes shape. This basic round crystal, known as an ingot, is now cut into a rectangular shape. This is done for purely practical reasons. Later on, square-shaped solar cells can be installed much more effectively on the surface of a solar module. The ingots are cut into millimeter-thin slices using a very fine wire saw. The individual slices are called wafers and form the basis of each solar cell. Once the wafers have been cut, they are sent through a wash tunnel. This is because even the smallest piece of dust or dirt can compromise solar cell production. The wafer's surface is now very flat. Just like a mirror, many rays of light are reflected and can no longer be used to generate power. To prevent this reflection, the surface is etched and roughened in a chemical bath. If the cells are put under a microscope, one can see the resulting pyramid structure. With this fine pyramid structure, light is refracted multiple times, allowing incoming light to be used far more effectively. The next step in solar cell production is diffusion. Here, a negatively charged phosphorus layer is added to each wafer's positively charged layer. In an oven heated to some 900 degrees centigrade, phosphorus atoms are injected with the help of nitrogen. The gaseous phosphorus-nitrogen mix is deposited on the wafer. At the interface between positive and negative charge layers, the free charge carriers created by the light are released. This generates an electric current. But how is the power that is generated in the individual cells transported? A stamp presses a silver alloy onto the front of the cells. This creates the typical grid pattern. This silver coating ensures that the power can be transported later on. The solar cells are now complete. They can generate and transfer power. But each cell has a different level of electrical conductivity. In a series of tests, the cell's conductivity is evaluated and sorted. Following the test phase, the solar cells are assembled. The cells are soldered together in such a way that the voltage accumulates. In a process referred to as lamination, the cells are assembled behind a pane of glass. As a result, they are protected from the elements for more than 25 years. One solar module contains 60 cells. When a number of modules are connected to one another, a solar power plant is created. And power is generated from the sun and the sand.
In this video, we're going to describe the doping of silicon to produce P-type and N-type semiconductors. That means they conduct in certain conditions, and describe how sunlight interacts with semiconductors. So really, this is the solar panel video, and you can sort of get some impressions from your sort of real-world connotations of doping. Doping means having a foreign substance inside. So we're going to be mixing in some different elements with silicon to try and create some interesting properties that allow us to make photovoltaics. This video is really a great example of how our knowledge of how elements are and what their structure is like, how we can use that to create really incredible clean tech solutions. So the first thing we're going to talk about just is this selection of silicon. And basically, what we should realize is that the lower the ionization energy is of something, in other words, the less tightly it holds onto its electrons, thus the higher the conductivity. And as we know, electricity really is usually around the flow of electrons, not always, but quite often. And silicon is perfect as it is a semiconductor, so it has a medium ionization energy. So it doesn't hold too tightly, but it's not exactly a metal, which is really conductive either. So this means that we can sort of manipulate when we want it to conduct and when we don't. And we'll see how that sort of works for us. So let's get into taking a look at these pictures here. And just as a note, so remember we need freely moving charged particles for electricity. So the freely moving charged particle we're going to be talking about here are electrons. So let's start with the N-type, which is drawn here. What we do is we dope the silicon with a group 5 element. So any of the group 5 elements listed here, and in this case, in the picture, we're going to use antimony. And the reason that we use a group 5 one is because it has an extra electron that is free to flow. So in other words, all the group 5 have 5 valence electrons. And so what happens is they can use 4 of them for bonding, and then there's one that just is not bonding, so it's able to flow, and thus we can have electricity. So this extra electron increases conductivity. So with an N-type, you just want to remember that it's group 5 elements because of that extra electron. Now down here we have an example of the P-type layer. So here we have doping with a group 3 element. So any of the elements in group 3 here will work. And what we see here is if they're in group 3, they only have 3 valence electrons, so they form 3 bonds, and then really there's sort of a hole here. And what we call that is a positive electron hole. So what you can see is we have an extra electron and then a place for the electron to go. And we're going to show how that works in the next slide. So here we have a simple model of if we were to sort of do a cross-section of a photovoltaic cell or a solar panel. So up here we have our N-type layer. So this is the one that's doped with the group 5 element, so it has an extra electron, or many extra ones, but we're just going to draw one, and that's negatively charged. So, and then down here we have our P-type, which has sort of the positive electron holes. So these electrons are attracted to this other plate. They have a natural tendency to want to go here. Now, when we hook up a wire between the two and we add a resistor inside, or a load, that's the worst line I've ever drawn. Let's try that again. And that's not much better. But anyway, this could be a TV, this could be anything that you want to run, so we can have the energy flow towards it, and then the electron will continue down. So you can just sort of follow its path all the way back over here, where it fills in. Once it gets over here, it's going to fill in the electron hole because a P-type is doped with a group 3 element and leaves a hole. And so what happens is the electron's now down in here and has filled up the hole. Now if this were just to stop at this, we wouldn't have a full circuit. We need to complete the circuit, and we also need to make sure that we don't run out of electrons. Otherwise it would sort of imply that our solar panel would sort of run out of energy. So this is where sort of the amazing ingenuity comes in. What happens is the sunlight comes down into this layer here, and it strikes one of these electrons, and then it ionizes it so that it returns back to the N-type layer. So that sort of completes the circuit. So at this stage, the sunlight excites the electrons so that they can be ionized from the P-type layer and return to the N-type layer, and then we can repeat this cycle indefinitely, and that's why solar panels can have such long lifetimes of upwards of 20 years. So this is a really excellent way to gain energy in a completely clean way. The only sort of unclean part of this would be its manufacturing. So we'd have to clean up the manufacturing as well in order to make sure that it wasn't too environmentally destructive.